Pick up a fridge magnet and hold it a centimeter above a paperclip lying on a table. The paperclip jumps up, and something has just happened that should bother you more than it does. The entire planet Earth, every atom of it, pulling down on that paperclip, lost. It lost to a piece of metal you can hold between two fingers. Set against electromagnetism, gravity is weaker by a factor of 1, followed by 36 zeros. And that weakness is the reason nobody ever tells you the truth about it. Physics runs on two theories. Both are perfect. Neither has ever failed a test, and they cannot both be complete descriptions of the same universe. The only reason that contradiction has stayed politely hidden for 96 years is that gravity is far too feeble to force the issue, anywhere except two places. And in both of those places, our physics does not give a wrong answer. It gives no answer at all. Get comfortable. Hit subscribe if you're new here, because by the end of tonight, you will know exactly what a finished theory of gravity would hand us, and why it is nothing at all like the thing everybody promises. Now, let's slowly ease into this. Part 1. 2 rulebooks, and neither one is wrong. There is a seam running through everything you have ever been told about physics, and almost nobody points at it directly. The reason is not that it is secret. The reason is that it is inconvenient, and that it sits underneath the interesting parts rather than inside them. When someone explains black holes to you, they are using one theory. When someone explains atoms to you, they are using a different theory. Those two theories are not two chapters of the same book. They are two books, written in different languages, describing overlapping territory, and there is no page anywhere in either of them that explains how to read them together. Physics runs on general relativity and quantum field theory. Both are correct. That is the difficulty. If one of them were merely wrong, we would have thrown it out a century ago and moved on, the way we threw out the luminiferous ether and the caloric theory of heat and the crystalline spheres that were supposed to carry the planets. But neither of these has ever failed a test, not once, not in 110 years of increasingly hostile attempts to break them. Let me give you the record, because the record is what makes the situation strange rather than merely untidy. General Relativity was published in 1915. It says that gravity is not a force pulling things together. It says that mass and energy bend the geometry of space and time, and that objects moving through that bent geometry are simply traveling as straight as they can. The Earth is not being tugged toward the sun. The Earth is going straight, through a region where straight has been curved. That sounds like a poetic reframing, until you look at what it predicted. It predicted that the closest point of Mercury's orbit should drift around the sun by a small extra amount that Newton could not account for, 43 arcseconds per century, a quantity astronomers had measured and puzzled over for decades. Einstein's equations produced that number exactly, with nothing adjusted to make it fit. It predicted that starlight passing close to the sun would be deflected, and on the 29th of May 1919, expeditions to Brazil and to an island off the coast of West Africa photographed the stars around a total eclipse and found the deflection. It predicted that time itself runs slower, deeper in a gravitational field, and in 1962, physicists at Harvard dropped gamma rays down a 22.5-meter lift shaft and measured a frequency shift of about 2.5 parts in 1,000 million, which is what the theory said it would be. It predicted that radio signals grazing the sun would be delayed, and in 2002, the Cassini spacecraft confirmed that delay to about 1 part in 100,000. It predicted that two massive objects orbiting each other would radiate energy away as ripples in space-time, and the binary pulsar, discovered by Hulse and Taylor in 1974, has been spiraling inward at exactly the predicted rate ever since, losing about 76 microseconds from its orbital period every year. And on the 14th of September 2015, two detectors in Louisiana and Washington state felt a passing ripple directly from two black holes that had merged 1.3 billion years ago and radiated away 3 entire suns' worth of mass as pure gravitational waves in less than a second. That is one book, every prediction, confirmed. Some of them confirmed a century after they were made, by instruments the author of the theory could not have imagined. Now the other book. Quantum field theory was assembled in pieces between the 1920s and the 1970s, and it describes everything that is not gravity. It describes electromagnetism, the strong force that holds nuclei together, the weak force that governs certain kinds of radioactive decay, and every particle of matter you are made of. It does not describe a world of little balls. It describes a world of fields, quantities that exist everywhere at once, where what we call a particle is a localized excitation, a ripple, in one of those fields. And unlike general relativity, it is not deterministic, it gives probabilities. Its accuracy is not comparable to general relativity's. It is better. It may be the most precisely verified body of knowledge that human beings possess in any subject whatsoever. Consider one number. The electron has a magnetic moment, a measure of how it behaves as a tiny magnet. Quantum electrodynamics allows you to calculate that number from first principles, and the calculation is horrendous. It involves summing over an ever-growing family of ways the electron can interact with the vacuum around it. In 2023, a group at Northwestern, led by Gerald Gabriels, measured that number and compared it to the calculation. Theory and experiment agree to roughly 1 part in 10 million million. To put that in a form you can hold, it is as if you measured the distance from New York to Los Angeles and got the answer right to within the width of a human hair. And not by luck, repeatedly, in independent laboratories, over decades, with the agreement improving each time. So we have two descriptions of nature. One of them has never been wrong about anything large. The other has never been wrong about anything small. And here is the part that should make you sit up slightly, even lying in the dark. They cannot both be complete descriptions of the same universe. This is not a case of two theories that disagree about a number and need a tie-breaking experiment. That would be ordinary science, and we know how to handle it. This is something more awkward. The two theories do not disagree about an answer. They fail to share a vocabulary. Quantum field theory requires a fixed stage. In order to say what a quantum state is, in order to say that this happens and then that happens, in order to define what a particle even means, you need a space-time that sits there and holds still while the quantum drama unfolds on top of it. Everything about the mathematics assumes a rigid arena with a definite geometry and a definite notion of before and after. General relativity says there is no such arena. It says space-time is not the stage. It is one of the actors. It bends, it stretches, it ripples, it responds to everything in it, and everything in it responds to it. The geometry is not the setting for the physics. The geometry is the physics. Now put those two statements side by side and notice what you are being asked to do. You are being asked to build a quantum theory of the very thing that quantum theory needs to already be sitting still in the background. You are being asked to make the floor uncertain while standing on the floor to do the measurement. For most of a century, physicists have known this, and for most of a century, they have been able to work around it, because there is a loophole. The two theories almost never have to be in the same room, and the way that loophole works, and the reason it eventually closes, is where we are going next. Part 2. The piece that was only ever an accident. The reason you have never noticed the seam is that gravity is pathetically, almost comically weak. We do not usually describe it that way, because gravity is the force we feel most constantly. It is the thing that makes staircases tiring and dropped mugs break. It holds the atmosphere down. It keeps the Earth in orbit and the galaxy assembled. From where you are lying, gravity seems like the dominant fact of physical existence. It is the weakest force in the universe by an enormous margin, and the margin is worth stating precisely, because the size of it is the whole reason the two rulebooks have been able to coexist. Take two protons and put them next to each other. They repel each other electrically because they both carry positive charge, and they attract each other gravitationally because they both have mass. Compare the two effects. The electric repulsion is stronger than the gravitational attraction by a factor of about 10 to the 36th. That is a 1 followed by 36 zeros. There is no useful analogy for a number that size, but here is an attempt. If the gravitational attraction between those two protons were the width of a single atom, the electrical repulsion between them would stretch across the observable universe several times over, and that comparison still undersells it. You can demonstrate this at home without any equipment. Hold a small magnet a centimeter above a paperclip lying on a table and watch the paperclip jump up. The entire mass of the planet Earth, 6,000 million tons of rock and iron, every atom of it pulling down on that paperclip, loses to a magnet you can hold between two fingers. That is not a close contest. That is the whole planet being casually overruled by a piece of metal the size of a coin. Now, this weakness is exactly why the two theories have never had to be introduced to each other. Quantum effects become important when things are small and light. Gravitational effects become important when things are heavy. The universe, as far as our instruments have been able to check, does not seem to contain very many things that are both. An electron is quantum, but its gravitational field is so far below detectability that the number describing it is not a physics measurement, it is a joke. A star is gravitational, but it is far too large and far too warm to display quantum behavior as a single object. Everything you have ever seen, touched, or measured sits comfortably on one side of that divide or the other. So physicists do what any reasonable person would do. They use general relativity for the big things, they use quantum field theory for the small things, and the fact that the two are structurally incompatible never comes up, because the two are never required to describe the same event at the same time. There is a way to see just how carefully the universe has arranged this separation, and it involves a number that sits oddly among all the others in this subject. Physicists define something called the Planck mass, which is roughly the mass at which quantum effects and gravitational effects would be expected to become comparable in strength. Almost every quantity built out of the fundamental constants in this way is absurdly far from anything human. The Planck length is smaller than a proton by 20 orders of magnitude. The Planck time is a division of a second so fine that the number requires 44 zeros after the decimal point. The Planck mass is about 22 micrograms. That is roughly the mass of a flea's egg, or a large grain of pollen, or one of the smaller specks of dust drifting through the beam of light coming under your door. It is the one Planck quantity that lands squarely in the world you can see. And that is a genuinely peculiar situation, because it means the mass scale at which our two theories should have collided is sitting right there on the table, entirely ordinary, and yet nothing on that table is behaving strangely. The reason is that a speck of dust is not a single quantum object. It is a million atoms, jostling and interacting and constantly measuring each other, and that internal traffic destroys quantum behavior long before the mass gets large enough for gravity to notice. The two effects have been kept apart, not by a fundamental principle, but by the practical difficulty of assembling something both heavy and undisturbed. The care with which gravity itself has been checked in this regime is worth a moment too, because it removes an easy escape route. One might hope that gravity is quietly behaving oddly at small scales, and we simply have not looked. We have looked. The equivalence principle, the statement that all objects fall at precisely the same rate, regardless of what they are made of, has been tested by orbiting satellites to a precision of about 1 part in 1,000 million, comparing test masses of different composition in free fall. No deviation has ever appeared. Whatever is wrong with our picture of gravity, gravity is not sending us hints in the places we have been able to search. In a hydrogen atom, the gravitational attraction between the proton and the electron is a real quantity that a person can calculate. It has simply never mattered. Nobody has ever measured it. Nobody expects to. The electric force between them is stronger by that factor of 1,000 million, and everything the atom does is governed by the electric force. Gravity is present in the equation and utterly irrelevant to the answer. Here is where I want you to make the turn with me, because this is the point where a comfortable arrangement starts to look like an unearned one. The peace between our two theories is not a discovery about nature. It is a description of our neighborhood. Think about what has actually been established. It has not been established that quantum theory and gravity are compatible. It has been established that we happen to live among objects that never force the question. That is an entirely different claim, and it is much weaker, and it depends on a fact about our circumstances rather than a fact about physics. The universe is not obliged to keep providing us with that convenience. There is nothing in either theory that promises the divide will always hold. The divide is a statement about the masses and sizes of the things in our immediate vicinity, the atoms, the planets, the stars, and the moment nature produces something that sits on both sides at once, the arrangement collapses, and both theories are compulsory simultaneously. And nature does produce such things. It has produced them at least twice, and both of those times matter more than anything else in the history of the universe. There is a useful way to think about what is coming. Imagine two people who have shared a house for 90 years without ever speaking, because one works nights and the other works days, and their schedules have never overlapped. You might describe that as a peaceful household, but you would not, if you were being careful, describe it as a functioning relationship. You would say the question has never been asked, and you would probably be slightly curious about what happens on the first morning one of them comes home early. The universe has come home early exactly twice. Once at the very beginning of everything, and once every single time a large enough star runs out of fuel and falls in on itself. Those are the two places where an object is heavy enough to demand general relativity and small enough to demand quantum mechanics in the same instant, in the same region, about the same thing. At those two places, our physics does not give a slightly wrong answer that we might refine later. It gives no answer at all, and what it gives, instead of an answer, is the subject of the next part. Part 3. The two places nature refuses to keep them apart. A star spends its entire life doing one thing, and that one thing is holding itself up. Gravity is trying to pull every part of it toward the center. The heat of nuclear fusion in the core pushes outward and resists. A star is a balance between those two pressures, and it stays in balance for as long as it has fuel to burn. Our own sun has been doing this for 4,500 million years and has about 5,000 million left. But fuel runs out. And when a sufficiently large star exhausts its fuel, the outward push stops, and nothing is left to resist the inward pull. The core falls. It falls faster than anything you have ever seen fall, because there is nothing beneath it and nothing holding it back. For a star of moderate size, the collapse eventually stops. Electrons refuse to be squeezed into the same quantum state as each other, and that refusal, a purely quantum effect, with no equivalent in classical physics, creates a pressure that halts the fall. You get a white dwarf, an object with the mass of the sun compressed into something roughly the size of the Earth. Push harder, with a heavier star, and the electrons lose. They are forced into the protons, and you get neutrons, and the same quantum stubbornness reasserts itself at a much higher density. You get a neutron star, the mass of a sun and a half inside a sphere you could drive across in 20 minutes, where a teaspoon of the material would weigh as much as a mountain range. Push harder still, and the question becomes serious, because there is nothing left to push back with. What Roger Penrose proved in 1965 is that at this stage, general relativity does not describe a very dense object. It describes a runaway. Once the collapse passes a certain point, the equations say there is no configuration of matter, no pressure, no force of any kind that can stop it. The collapse continues all the way down, and all the way down means to zero size and infinite density. The proof mattered enormously, and it mattered for a reason that is easy to miss. Before Penrose, this outcome was widely regarded as a mathematical artifact. The known solutions that produced it were perfectly spherical, and nothing in the real universe is perfectly spherical. Surely a slight lopsidedness, a bit of rotation, a little turbulence would cause the infalling matter to miss the exact center and swirl around it instead. Surely the infinity was an artifact of an unrealistic assumption. Penrose showed that it was not. Using the geometry of light rays, rather than assumptions about the matter, he demonstrated that once a certain kind of surface forms, a region from which even outgoing light is dragged inward, the singularity is unavoidable. It does not require symmetry. It does not require any particular kind of matter. It follows from the geometry itself. In 1970, working with Stephen Hawking, he extended the argument, and the extension pointed in a direction that had nothing to do with stars. Roger Penrose received the Nobel Prize for that work in 2020. He had published it 55 years earlier. Now I need you to be careful about what the word infinite is doing in that sentence, because almost everyone hears it wrongly, and the misunderstanding is the difference between finding this interesting and finding it merely dramatic. When a theory in physics produces an infinity, that is not a result. That is not the theory telling you there is a place in the universe with infinite density, the way it might tell you there is a place with a temperature of 10 million degrees. Infinity is not a number. It is a theory admitting it has stopped speaking. Every time this has happened before, it has meant the same thing. In the late 1800s, classical physics predicted that a hot object should radiate an infinite amount of energy at short wavelengths, the so-called ultraviolet catastrophe. That infinity was not a discovery about hot objects. It was a signal that classical physics was being applied somewhere it did not belong, and the resolution, when Max Planck found it in 1900, was the beginning of quantum mechanics. It said, "There is new physics here, and you have walked past the boundary of the old physics without noticing." So when general relativity predicts an infinity at the center of a collapsed star, the honest reading is not that reality becomes infinite. The honest reading is that general relativity has walked past its own boundary and is now producing noise. And the theory is unusually forthcoming about this. The singularity theorems are not a case of physicists finding a flaw and reluctantly admitting it. They are a case of the theory containing, within itself, a rigorous proof that it will fail, together with precise directions to the place where it happens. That is one location. Now run the film backwards, and you find the other. The universe is expanding. Every galaxy outside our local group is getting further away, and the further away it already is, the faster it recedes. Reverse that expansion, and everything gets closer together, hotter, denser. Keep reversing. The galaxies dissolve into the gas they formed from. The gas becomes a plasma too hot for atoms to hold together. The nuclei come apart into their constituent particles. Keep going, and the density climbs past anything the universe contains today, past the density of a neutron star, past the density inside a proton, and general relativity, run backwards far enough, arrives at exactly the same place it arrived at inside the collapsing star. Infinite density, zero size, no further statement available. This is what the 1970 extension was for. Penrose's original argument was about a star collapsing inward, and it turned on the formation of that particular kind of surface where outgoing light no longer escapes. Working together, Hawking and Penrose generalized the machinery so that it applied to the universe as a whole, treating the entire expanding cosmos as a collapse viewed in reverse. The conclusion was the same, and it was reached by the same route. Given an expanding universe containing ordinary matter, and given that general relativity holds, a singularity in the past is not one possibility among several, it is a theorem. We call that the Big Bang, and the name has done real damage, because it makes people picture an explosion, a moment, a bang, material flying outward into surrounding space. That is not what the mathematics says. The mathematics says that as you run the clock backwards, the theory that has correctly described every stage of cosmic history stops being able to say anything at all, and it stops at a specific moment. And that moment is roughly 13,800 million years before this evening. So we have found the two places. One is the end of a heavy star, and there are somewhere between 100 million and 1,000 million of them in our galaxy alone. The other is the beginning of everything that exists, including you. Both are regions where an enormous amount of mass and energy is compressed into a space small enough that quantum mechanics is compulsory. Both are therefore regions where you need both rulebooks at once, and at both, the theory we have for the heavy half returns a symbol rather than a number. The obvious response to this situation is to build the theory that covers both. People noticed the problem early, and they tried the obvious thing, and the obvious thing had already been tried and had already failed before most of the people currently working on it were born. How it failed, and why the way it failed, matters more than the fact of it, is the next part. Part 4. The calculation that ended the obvious approach. The first person to try to quantize gravity did it in 1930, which means this problem is 96 years old. His name was Leon Rosenfeld, and he was working at a moment when quantum mechanics was barely 5 years old and had just been spectacularly successful at describing the electromagnetic field. The reasoning was straightforward and, at the time, entirely sensible. Electromagnetism is a field. We have just learned how to make a field quantum. Gravity is a field. Do the same thing to gravity. He tried. He found infinities. And that outcome was not alarming at first, because the electromagnetic version had also produced infinities, and physicists were in the middle of learning how to tame them. A few years later, a Soviet physicist named Matvei Bronstein looked at the problem properly and reached a much more troubling conclusion. In papers published in 1935 and 1936, he argued that gravity was not going to yield to the same treatment as electromagnetism, because gravity is coupled to the geometry of space-time in a way that no other field is, and that quantizing it would require giving up the ordinary concepts of space and time altogether. He was 29 years old, and he had identified, essentially correctly, the shape of a problem that would still be open 90 years later. Bronstein was arrested in the Soviet Union in 1937 and executed in 1938 at the age of 31. His work went largely unread for decades. The field as an organized discipline really begins in 1957 at a conference in Chapel Hill, North Carolina, on the role of gravitation in physics. Richard Feynman was there, and he made an argument that people still use today. Suppose gravity is not quantum. Suppose it is a classical field, sitting in the background, definite at all times. Then take a particle and put it into a superposition of two paths. Its gravitational field, being classical and definite, would have to take one value or the other. And that means you could read the gravitational field to find out which path the particle took without disturbing it, which would destroy the interference pattern that quantum mechanics insists must be there. So either gravity is quantum, or quantum mechanics is wrong about something we have tested 10,000 times. Feynman's argument is not a proof, and physicists still debate its loopholes. But it is the reason nearly everyone assumes gravity must be quantized, even though no experiment has ever shown a quantum gravitational effect. Given that assumption, the program was clear. You do to gravity exactly what worked for the other three forces. Here is what that means concretely. Take space-time and write it as two pieces, a flat, rigid background plus a small ripple on top of it. Treat the ripple as the thing that carries the gravitational interaction. Quantize the ripple the way you would quantize any other field, and you get a particle, massless, traveling at the speed of light, carrying 2 units of spin. Call it the graviton. Then calculate. Calculating in quantum field theory means summing over possibilities. The simplest process is 2 particles interacting once, but quantum mechanics requires you to include every way the interaction could have happened, including ones where extra particles briefly appear and vanish along the way. Each additional layer of that complication is called a loop, and each loop makes the calculation dramatically harder, and each loop tends to produce infinities that must be absorbed by adjusting a small number of constants, the mass, the charge, against experiment. That absorption procedure is called renormalization, and it is the technique that made quantum electrodynamics the most accurate theory in science. The question for gravity was simple. Does the same absorption work? In 1974, Gerard Hooft and Martinus Veltman ran the one-loop calculation for pure gravity, and the answer came back encouraging. At one loop, the infinities cancel. Pure gravity, at the first level of quantum correction, is finite. That result was genuinely exciting, and for about a decade, the possibility that gravity might simply behave itself was live. The two-loop calculation was the test, and it was, by any reasonable standard, monstrous. The algebra involved in expanding Einstein's equations to second order in quantum corrections produces expressions with tens of thousands of terms. No human being can do it by hand and be confident of the answer. Picture a room in the middle of the 1980s. There is a terminal and the green characters of a printout, and 2 physicists named Mark Goroff and Augusto Sagnotti, who have spent months not doing physics in the way it is usually pictured, but writing computer code, programs in C, built specifically for this, because nothing existing could handle the size of the expressions. The machine grinds. It has been grinding for a long time. The question it is answering is not a small technical detail. The question is whether the universe permits the obvious approach to the deepest problem in physics. They are looking for a coefficient. If that coefficient is 0, the infinities cancel again at 2 loops, gravity is well behaved, and the problem that has been open since 1930 is on its way to being solved. If it is not 0, the approach is finished. The result comes back. It is not 0. The paper was published in 1986 in Nuclear Physics B under the deliberately flat title The Ultraviolet Behavior of Einstein Gravity. The divergent term was a particular product of 3 factors of the curvature tensor, and there was no way to absorb it. 6 years later, in 1992, an independent calculation by another physicist confirmed it. The result has stood ever since. Now, what exactly did that kill? This is the part that is almost always described badly, and getting it right changes what the rest of this evening is about. It did not show that gravity is not quantum. It did not show that general relativity is wrong. It showed something more specific and more frustrating, that when you treat gravity as a quantum field theory in the standard way, the theory requires an endless supply of adjustable constants. At one loop, none. At 2 loops, 1. Go to higher loops, and you need more, and there is no point at which the list ends. A theory with a small number of free parameters is a theory that makes predictions, because once you have fixed the parameters with a few measurements, everything else follows and can be checked. A theory with infinitely many free parameters can be fitted to absolutely any observation you make, and therefore forbids nothing, and therefore predicts nothing. It is not false, it is empty. There is an important consolation here, and leaving it out would give you a bleaker picture than the truth deserves. The failure is confined to high energies. At the energies of ordinary life, the energies of falling apples, orbiting moons, colliding neutron stars, and anything else the universe has ever shown us, the same machinery works perfectly well, provided you use it modestly. Physicists call this treating gravity as an effective field theory, which means accepting that the description will break down somewhere far above the energies you care about, and calculating only up to that point. Used this way, quantum gravity is not unknown. It is calculable. There is a definite, computed quantum correction to Newton's law of gravitation, a tiny modification to the force between two masses arising from the same kind of virtual particle activity that produces the electron's magnetic moment. The number is real, it has been worked out in detail since the 1990s, and it is utterly hopeless to measure, being smaller than the classical effect by a factor related to the square of the ratio between the separation and the Planck length. So the situation is not that we have no quantum theory of gravity. It is that we have one which works everywhere, except the two places we actually need it. It is a map that is accurate across the entire continent and blank in exactly the two locations where the treasure is buried. Below the Planck energy, the theory is quiet and cooperative. At the center of a black hole and at the first instant of the universe, the energies climb to precisely the scale where the infinite list of unknown constants starts to matter, and every one of those constants would have to be measured before the theory could tell you anything. That is what failed in 1986. Not the answer, but the possibility of getting an answer by that route. And what makes it more than a technical setback is that the failure has a reason, a specific structural feature of gravity that no other force shares. Understanding that feature is understanding the whole problem, and that is where we go next. Part 5. The only force that is also the room. There is a reason gravity behaves differently from the other three forces under this treatment, and once you see it, you cannot stop seeing it. Let me build up to it carefully, because it involves a piece of mathematics that sounds dry and turns out to be the entire problem in disguise. Every force in physics has a coupling constant, a number that says how strongly it acts. For electromagnetism, that number is the fine structure constant, roughly 1/137. It is a pure number. It has no units. It is not 1/137 meters, or seconds, or kilograms. It is simply a ratio, the same in any system of measurement anyone could invent. That fact is not a curiosity. It is the reason quantum electrodynamics works. When you calculate in quantum field theory, each additional loop brings another factor of the coupling constant. If the coupling is a small pure number, each loop multiplies your answer by something small, and the series of corrections gets smaller and smaller and settles down. The first correction is a small adjustment. The second is a small adjustment to the small adjustment. You can compute a few terms, stop, and be confident that everything you left out is negligible. That is why the electron's magnetic moment can be predicted to 13 decimal places. Now look at gravity's coupling constant, which is Newton's gravitational constant. It is not a pure number. It carries units, and when you write it in the natural units physicists use for this kind of work, those units come out as a length squared. That single fact is the whole difficulty. Because if the coupling carries units of length squared, then in order to produce the dimensionless quantity, that a calculation actually requires, it has to be multiplied by something else with units, and the only thing available is the energy of the process. So the effective strength of gravity in a quantum calculation is not a fixed number. It is Newton's constant times the energy squared. It grows as the energy grows. Turn that over and consider what it means. For electromagnetism, going to higher energy, probing smaller distances, leaves the coupling essentially unchanged and the corrections stay tame. For gravity, every step toward smaller distances makes the interaction stronger, which makes the next correction larger than the last one, which makes the one after that larger still. The series does not settle down, it runs away. And there is a specific energy at which the running away becomes total. When the energy is high enough that Newton's constant times the energy squared reaches about 1, every term in the series is roughly the same size as every other term, and the entire method of calculating by successive small corrections becomes meaningless. That energy is the Planck energy, and it is about 1.22 times 10 to the 19th giga-electronvolts. It is worth pausing on how much energy that is, concentrated into a single particle. The Planck energy is roughly what you would get if you took the chemical energy released by burning a full tank of petrol in a car and packed all of it into one proton. Nothing in the universe today does this. Nothing has done it since the first fraction of a second after the beginning. So the infinities we met in the last part are not a random misfortune. They are the fingerprint of a coupling that strengthens without limit as you look closer. Gravity is not badly behaved at high energy by accident. It is badly behaved by construction, and the construction is Einstein's. And the same feature that makes the theory beautiful at large scales is what makes it intractable at small ones. There is a second feature that compounds this one, and it is worth naming because it is the reason gravity is difficult even before you get anywhere near the Planck energy. Gravity couples to energy, not to a special charge that only some things carry, but to energy itself, which everything has. Electric charge is selective. A neutron has none, a photon has none, and so the electromagnetic field can pass straight through great quantities of matter without noticing it. Gravity has no such selectivity. Anything with energy gravitates, and anything with energy responds to gravity, and there are no exceptions anywhere in physics. Now apply that rule to the gravitational field itself. The gravitational field carries energy. Therefore, the gravitational field gravitates. Therefore, gravitons interact with other gravitons, which produce further gravitons, which interact in turn. Compare that to light. Two beams of light cross in a dark room and pass through each other without the slightest interaction, because photons carry no electric charge and are therefore invisible to the field they mediate. You can shine a torch through a laser beam, and neither one cares. Gravity is not like this at all. Two gravitational waves crossing do interact, faintly but genuinely, because each one carries energy, and energy is what gravity responds to. This self-interaction is why Einstein's equations are nonlinear, and nonlinearity is the technical reason the two-loop calculation was monstrous rather than merely tedious. In electromagnetism, you can add solutions together and get a solution. In gravity, you cannot. The field feeds back on itself at every level, and the feedback is what generates the ever-expanding cascade of terms that Goroff and Sagnotti needed custom software to handle. So gravity arrives at the problem with two burdens that no other force carries. Its strength grows with the energy of what you are probing, so the corrections escalate instead of settling. And it talks to itself, so every correction breeds further corrections. That is the technical statement. Now here is the deeper one, and it is the sentence I would like you to carry through the rest of tonight. Electromagnetism happens in space-time. The strong force happens in space-time. The weak force happens in space-time. Gravity does not happen in space-time. Gravity is what space-time does. Gravity is the only force that is also the room. Sit with that for a moment, because it is not wordplay. Every other field in physics is something laid down on top of the geometric arena, a value assigned to each point of a stage that is simply given, that was there before the field arrived and remains there after. When you quantize the electromagnetic field, you make the values uncertain, you allow them to fluctuate, you let them exist in superpositions. And through all of that, the stage holds still. The points are still points. The distances between them are still definite. There is still a well-defined answer to whether this happened before that. In general relativity, there is no such stage. The geometry is the gravitational field. There is nothing underneath it. Space-time is not the container that gravity acts within. Space-time is the thing that is doing the gravitating. Take gravity away, and you do not get an empty arena. You get nothing at all. No distances, no durations, no locations, no arena to be empty. So quantizing gravity means making the room itself uncertain. It means allowing the distance between 2 points to be in a superposition of 2 values. It means allowing the question of which of 2 events happened first to have no definite answer. And you have to do all of that using a mathematical framework whose every operation assumes that distances are definite and that the order of events is fixed, because that framework was built for fields living on a stage. This is why the difficulty is structural rather than technical. Nobody is failing to be clever enough. The method consumes its own foundation. It is like being asked to weigh a set of scales using only that set of scales, or to translate a dictionary using only that dictionary. Not impossible in principle, perhaps, but not solvable by pushing harder at the obvious approach, because the obvious approach has a circle at the center of it. And the circle is not merely philosophical. It shows up as a hard mathematical fact the moment anyone tries to write the equations down properly. When physicists take general relativity, put it into the form required for quantization, and turn the handle, they get an equation that is genuinely strange. An equation that describes the quantum state of an entire universe, and that appears, on inspection, to say that nothing in that universe ever changes. That equation is where we are going next, and it is the point in this story where the ground under the question dissolves. Part 6. The equation where the clock disappears. In 1967, Bryce DeWitt and John Wheeler wrote down what a quantum theory of the entire universe would have to look like. They did it the honest way. They took general relativity, put it into the form that quantization requires, applied the standard procedure that had worked for every other system anyone had ever quantized, and looked at what came out the other end. The result is called the Wheeler-DeWitt equation, and it is the closest thing physics has to a Schrödinger equation for everything that exists. To see why it is disturbing, you have to know what the ordinary Schrödinger equation says. It says, here is the quantum state of a system, and here is how that state changes as time passes. Time is the parameter. Time is the thing on the left-hand side of the arrow. Everything in quantum mechanics, probabilities, evolution, measurement, the whole apparatus, is organized around the idea that a state at one moment becomes a different state at a later moment. The Wheeler-DeWitt equation contains no time, not a subtle version of time, not a modified or emergent or relativistic version of time. The variable is simply absent. The equation says that a certain operator, applied to the wave function of the universe, gives 0. There is no term describing how anything changes, because there is no parameter with respect to which anything could change. Read literally, the equation describes a universe that does not evolve, a single, frozen, timeless quantum state containing everything. Now, the technical reason this happens is not mysterious once you see it. In general relativity, Time is not a background parameter that ticks along independently. Time is part of the geometry. It is one of the things the theory is describing, rather than one of the things it is described against. And the theory has a symmetry. You are free to relabel the time coordinate however you like, without changing any physical content. Nothing measurable depends on your choice of clock. When you quantize a system with that kind of symmetry, the symmetry turns into a constraint, and the constraint says that the total energy of a closed universe is zero. Not small. Exactly zero as a matter of principle, because the positive energy of all the matter is precisely cancelled by the negative energy of the gravitational field it creates. And in quantum mechanics, energy is what generates change over time. Zero energy means no generator of change. No generator of change means no evolution. The universe, on this reading, does not have a total energy that could power a clock, because it does not have an outside for the clock to tick relative to. I want to be careful here, because this is a place where it is easy to overstate. The Wheeler-DeWitt equation is not established physics. It has serious mathematical problems. It is not well defined in the form Wheeler and DeWitt wrote it, and making it rigorous is one of the things loop quantum gravity has spent decades on. Nobody claims it is the final word. But it was obtained by doing the obvious and honest thing, and the disappearance of time from it is not a mistake somebody made. It is a structural consequence of taking both theories seriously at once, and it appears in some form in essentially every approach to the problem. Physicists call it, without much drama, the problem of time. And the resolutions that have been offered are as strange as the problem. The best known was proposed by Don Page and William Wouters in 1983. Their suggestion is that time is not fundamental, it is relational. Divide the universe into two parts. Call one part the clock, and the other part everything else. Neither part has a time variable of its own, but the two parts are entangled, and if you ask a conditional question, given that the clock subsystem is in this configuration, what state is the rest of the universe in? The answer changes as you step through the clock's configurations. The universe as a whole does not evolve, but viewed from inside, correlated with a subsystem that serves as a clock, it appears to. Time is not something the universe has. Time is something that appears when you look at part of the universe from inside another part of it. In 2013, a group in Italy built a small laboratory illustration of exactly this, using entangled photons, a toy universe of two particles, in which an internal observer sees evolution, and an external one sees a static state. It is a demonstration of the logic, not evidence about the real universe. But watching the idea work in a laboratory makes it much harder to dismiss as a philosopher's move. Carlo Rovelli has pushed a related line for decades, that there is no such thing as time in the fundamental description, only relationships between physical variables, and that what we call the flow of time is a thermodynamic effect arising from our coarse-grained ignorance of the details. There is a companion problem sitting right beside this one, and it is arguably worse, because it attacks the idea of superposition rather than the idea of time. Take a small object and put it into a superposition of two positions. This is not exotic. It is done routinely with atoms, and it has been demonstrated with molecules containing thousands of atoms. Now ask what its gravitational field is doing. If gravity is quantum, the answer has to be that the field is in a superposition too, a superposition of the geometry produced by the object being here and the geometry produced by it being there, which means space-time itself is now in two configurations at once. And the moment you write that sentence, you have a problem, because superposition is defined by addition. To say that a system is in a superposition of two states is to say that you add those two states together. But adding two states requires knowing which point in the first state corresponds to which point in the second, and requires a shared notion of what "at the same time" means, so that you know which moment of the first geometry to add to which moment of the second. In two different geometries, those correspondences do not exist. There is no fact about which point of one curved spacetime is the same point as which point of another. The identification you need in order to perform the addition is exactly the thing that the two states disagree about. So the operation at the heart of quantum mechanics turns out to be undefined for the one field that determines what the operation means. This is the circularity from the last part, appearing now not as a philosophical observation, but as a specific place where the mathematics stops working. Quantum theory needs a background in order to define superposition. Gravity is the background, and you are being asked to superpose it. Now let me bring this out of the mathematics and put it where it actually lands. You have never for one moment doubted that time is real. It is the most immediate fact of being conscious. You remember the earlier part of this evening and not the later part. You are waiting for sleep, which is ahead of you. Every plan you have ever made, every regret you carry, every expectation about tomorrow rests on the assumption that there is a genuine, mind-independent flow, that now is a real feature of the world and not a description of your position in it. And the leading attempt to write down a quantum description of the universe produces an equation in which nothing evolves at all, in which now is not fundamental, in which the sense of passage you have been experiencing continuously since you woke up this morning would be a derived quantity, something that emerges from how one part of the universe is correlated with another, in roughly the way that temperature emerges from the motion of molecules that do not individually have a temperature. I am not telling you that this is true. Nobody knows that it is true. What I am telling you is that our best attempt to combine our two best theories does not rule it out, and in fact seems to lean toward it. The most undeniable feature of being alive may turn out to be an artifact of the point of view. So we have arrived somewhere genuinely uncomfortable, and I think this is the right moment to stop climbing and take stock of what we have actually found. Because it is not one problem, it is four, and seeing them stacked together is what makes the rest of tonight possible. Part 7. 4 problems, not one. Let us stop for a moment and put the pieces on the table together, because we have been climbing steadily, and it is worth seeing the shape of what we have found before we go further. When people say gravity has not been solved, it sounds like a single missing equation, something a sufficiently gifted physicist might one day write on a blackboard. What we have actually accumulated over the last hour is not one gap. It is 4 distinct failures, and they fail in different directions, which is why patching any one of them does not fix the others. The first is the infinities. Treat gravity like every other force, and the calculation demands an endless supply of adjustable numbers, and a theory that needs infinitely many numbers put in by hand is not a theory that forbids anything. That was settled in 1986, and it was settled by a coefficient that came back not equal to 0. The second is the missing background. Every other quantum field lives on a stage. Gravity is the stage. There is nothing underneath it to lay it down on, and the standard method of quantization has no idea what to do with a field that constitutes the arena rather than occupying it. The third is the missing time. Do the procedure honestly, and you get an equation for the universe with no time variable in it, a description in which nothing evolves, and in which the sense of passage you are experiencing right now would have to emerge from correlations between parts of a static whole. And the fourth is one I have only gestured at, so let me state it plainly. In ordinary quantum mechanics, there is an unresolved question about measurement, about what actually happens when a superposition becomes a definite outcome, and about the role of the observer and the apparatus in producing it. Physicists have argued about this for 100 years, and in practice, they have been able to set it aside, because there is always an outside, there is always a laboratory, an instrument, an environment that is not part of the quantum system. A quantum theory of gravity is a quantum theory of the whole universe, and there is no outside. No external apparatus, no external environment, no external clock. The measurement problem, which was awkward and postponable in every other context, becomes unavoidable and structural the moment the system under description is everything. 4 problems: infinities, no background, no time, no outside. And it is worth understanding why they cannot be attacked as a group, because this is the practical reason the field has produced so many partial answers. The approaches that are best at curing the infinities tend to do it by putting gravity back onto a fixed background, which surrenders the second problem in order to solve the first. The approaches that take background independence most seriously tend to struggle to recover ordinary smooth spacetime at everyday scales, which is a different way of failing. The approaches that treat time as emergent make progress on the third problem while saying very little about the first. Each candidate is strong precisely where the others are weak, and no one has yet produced a framework that is strong everywhere at once. There is arguably a fifth leak too, and it is the largest numerical disagreement anywhere in science. Quantum field theory says empty space should carry an energy density, and general relativity says that energy density should make the universe expand at a particular rate. Do both calculations and compare the answer to what the universe actually does, and the theoretical estimate overshoots the observed value by something in the region of 120 orders of magnitude. That is not a discrepancy in the ordinary sense. There is no other number in physics that is wrong by a factor with 120 zeros in it, and it sits exactly on the seam in the one calculation that requires both rulebooks at once. Notice what they have in common, because this is the reassembly I want you to take with you. Every one of them is a description that is currently missing. Not a wrong description that needs correcting. A place where our physics produces silence rather than a sentence. At the center of a collapsed star, silence. At the first instant, silence. On the question of what when means at the bottom, silence. On the question of what happens when the universe as a whole is treated quantum mechanically, silence. Infinity is not a number. It is a theory admitting it has stopped speaking. And what we have actually catalogued tonight is 4 different rooms in which the theory has stopped speaking, which turns the question inside out. And this is where the second half of tonight begins. Because if the situation is that 4 descriptions are missing, then the interesting question is no longer only why they are missing. The interesting question is, what arrives when they are supplied? What is the sentence that replaces the silence at the center of a black hole? Not, we do not know. What does a working theory actually say is there? What is the sentence that replaces the silence at the first instant? Is there a before? And if the answer is no, what is the correct thing to say instead? If the past is being erased when things fall into black holes, does a completed theory say that erasure is real, or does it say the record survives? And if space-time is not fundamental, then what is it made of? And what is the room you are lying in actually a description of? Those are the 4 questions, and they are the reason this problem matters to anyone who is not a theoretical physicist, because none of them is currently unanswered in the ordinary sense. They are worse than unanswered. They are improperly posed. There is no framework in which they can even be asked in a way that admits an answer, which is why every popular attempt to describe the inside of a black hole trails off into metaphor. Solving gravity would change that. It would take 4 questions that are currently not even legitimate and turn them into questions with answers, and then it would supply the answers. So for the rest of tonight, we are going to walk through them one at a time. What is inside? Whether the past survives, what came before, and what space itself is made of. And then, at the very end, we will come back to the question in the title. What actually happens when we solve it? Because the honest answer is not any of those 4. It is something underneath all of them, and it is stranger and quieter than any of the things people usually promise. But we are not ready for it yet. We need to walk through the four first. Start with the one you can almost picture. Start with what is inside a black hole. Part 8. What is actually inside a black hole? Nobody knows what is inside a black hole, and the reason is not that it is far away or hard to see. We have photographed two of them. On the 10th of April 2019, the Event Horizon Telescope collaboration released an image of the shadow of the supermassive black hole at the center of the galaxy M87, assembled from radio telescopes spread across the surface of the Earth. On the 12th of May 2022, they released an image of the one at the center of our own galaxy. Both images match the geometry general relativity predicts to a satisfying degree, and both images stop at exactly the same place for exactly the same reason. The horizon is not a surface. It is a boundary in the causal structure of space-time, the locus of points from which no path, not even a path traveled at the speed of light, leads back out. Every photograph of a black hole that will ever be taken is a photograph of the outside. There is no observational program, however ambitious, that returns information from the interior, because no information returns from the interior is the definition of the object. So the only access we have is theoretical, and the theory we would use has, as we established, stopped speaking. Before we go in, there is a confusion worth clearing away, because almost everyone carries it, and it makes the rest of this harder than it needs to be. The horizon and the singularity are not the same thing, and they are not even close to each other. The horizon is a boundary defined by escape. Its size depends only on the mass. For the Sun, if the Sun could somehow be compressed enough to have one, the horizon would be about 3 kilometers across. For the black hole at the center of our galaxy, roughly 4 million times the mass of the Sun, the horizon is about 24 million kilometers across, which is comfortably larger than the orbit of Mercury. And here is the counterintuitive part. As black holes get larger, the average density inside the horizon goes down, because the horizon grows in proportion to the mass, while the volume it encloses grows as the cube of that. For a black hole of a few 100 million solar masses, the average density inside the horizon is less than the density of water. If you could hold a sphere of that region in your hand, it would feel like nothing much at all. The horizon is not a dense object. It is a geometrical statement about where the light cones point. The singularity is a different thing entirely, sitting far inside, and it is the singularity, not the horizon, that our physics cannot describe. So when I say we do not know what is inside a black hole, I do not mean that the region behind the horizon is uniformly mysterious. General relativity describes most of that region perfectly well. It is the last stretch of the journey, deep in, where the description gives out. Let me show you what that actually feels like, and I want you to come with me for this, because the differences between the candidate answers are not differences of detail. Imagine you are falling. You have chosen a large black hole, a supermassive one, because the tidal forces at the horizon of a large black hole are gentle enough that you cross it without noticing. There is no wall, no flash, no membrane. You pass the point of no return, and nothing whatsoever happens to you in that instant. The stars behind you are still visible, crowded now toward a shrinking circle, and you continue to fall. Now, what happens next depends entirely on which theory is right, and here is what each of them says. If general relativity alone is correct, the tidal forces begin to grow. The difference in gravitational pull between your head and your feet increases, then increases faster, then increases without limit. The curvature climbs toward infinity, and the description does not end with a bang or a crush or a final moment. It ends mid-sentence. The equations produce infinity, which is not an event you experience but a place where the mathematics stops producing statements. There is no answer to what happens after, because there is no after in the description, and there is no description. If loop quantum gravity is broadly right, something different happens. As the density climbs toward the Planck scale, the discreteness of geometry begins to matter. Space, in this picture, is not infinitely divisible, and there is a smallest possible volume that quantum geometry permits. And when you try to compress matter past that, the quantum structure of space pushes back. Not a force in the ordinary sense, but a consequence of there being no smaller configuration available. The collapse slows, stops, and reverses. The infinity is replaced with a bounce. If the fuzzball proposal from string theory is right, then the question you have been asking is malformed, because there is no interior at all. On this picture, the black hole is not empty space surrounding a singular point. It is a dense tangle of extended objects filling the entire volume out to the horizon, and the horizon is the surface of the object rather than a threshold you can cross. You never fall through. You arrive at a surface. And if the Planck star picture is right, then the collapse halts at an enormously dense but perfectly finite core, something with the mass of a dead star packed into a region on the scale of a grain of dust, held up by quantum geometric pressure, waiting on a timescale far longer than the present age of the universe to slowly re-expand. 4 answers. And notice, they do not disagree about a detail. They disagree about whether the word inside refers to anything at all. Infinity is not a number. It is a theory, admitting it has stopped speaking. And that phrase, which sounded in the earlier parts like a caution about mathematics, is now doing something more useful. It is telling you exactly what a quantum theory of gravity would deliver. It would replace a silence with a sentence. That is what solving gravity means in this case. Not a new capability, not an instrument, not access. Simply this. The place in the description where the theory currently trails off gets filled in with a specific, definite, checkable statement about what is there. The singularity is not a feature of black holes. It is a feature of our description of black holes, and every serious candidate for quantum gravity removes it. That is worth sitting with for a moment, because it is a genuine consensus in a field with very little of it. String theorists and loop quantum gravity researchers agree on almost nothing about method or philosophy. They agree that there is no singularity, the infinite density at the center of a black hole, which has been a fixture of popular science for 50 years, is almost universally expected to be an artifact, the same kind of artifact as the infinite radiation of the ultraviolet catastrophe, and destined to be resolved the same way. The precedent is exact, and it is worth spelling out, because it tells you how confident to be. At the end of the 1800s, classical physics predicted that a warm object should pour out infinite energy at short wavelengths. Nobody concluded that fireplaces emit infinite energy. Everyone concluded that the theory had been pushed past its domain. The infinity was a signpost pointing at undiscovered physics, and the physics it pointed at turned out to be quantum mechanics, the single largest expansion of human understanding of nature in the 20th century. The infinity at the center of a black hole is expected to be exactly the same kind of signpost, and the physics it is pointing at is the thing we do not yet have. There is even a faint hope of testing this, though it should be labeled clearly as speculation rather than established science. Some researchers working in loop quantum gravity have suggested that if collapse really does bounce, then a black hole would eventually turn inside out, becoming, after an extraordinarily long time, something that expels material rather than swallowing it. For the smallest primordial black holes, if any formed in the early universe, the timescale might be short enough that the transition is happening somewhere now, and might produce a brief, characteristic burst of radiation. Nobody has observed such a thing, and there is no consensus that the calculation is trustworthy. But it is one of the very few places where a quantum gravity proposal makes a statement that a telescope could in principle check, which is why it gets more attention than its confidence level strictly deserves. There is a further consequence, and it is less often mentioned. If the singularity is removed, then the interior of a black hole is a place. It has a physics. Things happen there according to laws, and those laws are in principle statable. It stops being a hole in the universe and becomes a region of the universe about which we are ignorant, which is an enormous change in status, even though from outside nothing looks any different. And that raises the question that turned out to be the deepest one in this entire subject. Not what is inside, but what happens to it. Because black holes are not permanent, and what leaks out of them has kept physicists arguing for 50 years about whether the past can be destroyed. Part 9. Whether the past survives. In 1974, Stephen Hawking found something that nobody expected, including him. He had been working on black holes using a hybrid approach, quantum fields on a fixed curved spacetime. Not a full quantum theory of gravity, which nobody had, but a halfway house. Let the geometry be classical, and let the matter fields be quantum, and see what happens. It is exactly the sort of approximation that ought to give reasonable answers, as long as you do not push too hard. What it gave was that black holes are not black. They glow. The mechanism is subtle, and every short description of it is slightly wrong, including the one I am about to give you. But here is the shape of it. Empty space in quantum field theory is not empty. It is full of activity, fluctuations of the underlying fields that cannot be switched off. Near the horizon of a black hole, that activity gets divided by the geometry itself. What one observer calls empty vacuum, another observer, falling differently through the same region, does not. The result is that a distant observer sees a genuine flux of radiation streaming away from the horizon with a genuine temperature. The temperature is tiny for anything large. A black hole of a few solar masses radiates at about a 10 millionth of a degree above absolute zero, far colder than the microwave background, which is why real black holes today absorb more than they emit. But the radiation is real, and it carries energy away, and energy is mass, so the black hole shrinks. Given enough time, for a stellar mass black hole, something like 10 to the 67 years, in a universe currently about 10 to the 10th years old, it evaporates entirely. It is gone, and here is where the trouble starts. Everything that fell in is gone with it. The star that collapsed, whatever wandered in over the aeons. And Hawking's calculation had a devastating feature. The radiation coming out is thermal. It is featureless. Its properties depend only on the black hole's mass, charge, and spin, and on nothing else whatsoever. Two black holes formed from completely different material, one from a collapsing star, one from an equal mass of encyclopedias, radiate identically and leave nothing behind to tell them apart. So the information about what went in has been destroyed, not hidden, not scrambled, not made impractical to recover. Destroyed. That sounds like a curiosity, and it is actually a catastrophe, because quantum mechanics does not permit it. One of the deepest structural properties of quantum theory is called unitarity, and what it means is that the underlying evolution of a quantum state is reversible in principle. If you knew the exact quantum state of a system now, and you knew the laws, you could run the equations backwards and recover the exact state at any earlier time. Information is never created and never destroyed. It gets spread around, scrambled beyond any practical hope of reassembly, but it is always in principle still there. Burn a book, and you feel as though the information is gone. It is not. It is in the smoke, in the ash, in the pattern of infrared radiation that left the fire, in the precise correlations between all those things. A sufficiently capable being, with perfect knowledge of the final state, could, according to quantum mechanics, reconstruct every word on every page. That is not a poetic claim. It is what unitarity says. Hawking's calculation said that black holes break this. And that is not a small correction to quantum mechanics. It is a violation of the property that makes the whole framework consistent. So physics had a genuine contradiction, and it had it in exactly the place we would expect, the one place where both rulebooks are compulsory at once. Hawking argued for the destruction of information for nearly 30 years. Others, particularly Leonard Susskind and Gerard Hooft, argued that quantum mechanics had to win and that the calculation must be missing something. The argument was long, public, and genuinely bitter at times. There had been a clue sitting there since before Hawking's paper. In 1972, Jacob Bekenstein had argued that black holes must carry entropy, a measure of the number of microscopic arrangements consistent with the object's large-scale appearance, and that the entropy is proportional to the area of the horizon. That is a very strange result, and its strangeness is easy to miss. Entropy normally scales with volume. Double the volume of a gas, and you double the number of ways to arrange its molecules. But a black hole's entropy scales with the area of its boundary, not the volume it encloses. The information content of the region is set by the size of the surface around it. Nobody knew what to do with that in 1972. It turned out to be the most important hint in the subject, and we will come back to it in the next part. The argument also produced one genuinely alarming intermediate result, worth mentioning, because it shows how tightly constrained the problem is. In 2012, a group of physicists pointed out that if you insist on unitarity, and you also insist that an infalling observer notices nothing unusual at the horizon, and you insist on a few other reasonable-sounding requirements, the requirements contradict each other. Something has to give. One way out is that the horizon is not gentle at all, but a wall of enormously energetic particles that incinerates anything crossing it, the so-called firewall. Almost nobody likes this answer, because it means general relativity fails badly in a region where the curvature is mild, and it should have no business failing. But nobody has been able to remove it cleanly either. And the fact that a paradox this sharp can be constructed from apparently modest assumptions is a good measure of how little room the problem leaves. The turning point in the argument itself came from Don Page, who asked a sharper question in 1993. Do not ask whether information comes out, ask when. If evaporation is unitary, then the entanglement between the radiation already emitted and the black hole still remaining must follow a specific curve, rising while the black hole is large, then turning over at about the halfway point and falling back to zero when the evaporation completes. That shape is now called the Page curve. Hawking's calculation produced a curve that rises and keeps rising, never turning over, so the two positions made different, definite predictions about a computable quantity, and the disagreement stopped being philosophical. In 2019, several groups working independently found that a more careful treatment of the same semsmechlackosal physics does produce the Page curve. The technique involves including contributions to the calculation that had been silently discarded, geometries in which regions deep inside the black hole, called islands, count as part of the radiation for the purposes of computing entropy, connected through what are called replica wormholes. I will not pretend this is settled or simple. The calculations are done in simplified models, the conceptual interpretation is actively disputed, and nobody would claim the information paradox is closed. But the direction has reversed. The current majority position, arrived at by calculation rather than by preference, is that black hole evaporation is unitary. Hawking himself conceded the point in 2004, famously paying off a bet with an encyclopedia. Now let me tell you what that means, away from the mathematics. Unitarity says that nothing that has ever happened is ever fully erased. Not hidden, erased. There is a difference, and the difference is everything. The universe permits things to become unrecoverable in practice. It does not, if this is right, permit them to become unrecoverable in principle. Every configuration that has ever existed leaves a record in the correlations of what came after, and the record persists, in a form no being could ever actually read, for as long as the universe lasts. The most complete destroyer that physics knows about, an object that swallows stars whole and leaves a hole in the sky, turns out not to destroy anything. It scrambles, over timescales longer than the present age of the universe, and then it hands everything back in a form nobody could ever decode. There is comfort in that, and there is something colder in it too, and I do not think you have to choose. The universe does not appear to permit forgetting. Not a star, not a page, not a person. Whether that is a consolation or a weight is a question physics does not answer, and it comes attached to the same theory we do not yet have. Which brings us to the other end of time, and the silence that sits at the beginning. Part 10. The first instant becomes a question with an answer. There is a wall about 13,800 million years behind us, and it is not made of anything. We can see almost all the way to it. The oldest light in the universe, the cosmic microwave background, was released about 380,000 years after the beginning, when the universe had cooled enough for atoms to hold together, and for light to travel freely for the first time. That radiation is still arriving, from every direction, and we have mapped its temperature variations to a precision of a few parts in 100,000. It is the most detailed photograph anyone has ever taken of anything. Behind that light, the universe was opaque, and no telescope will ever see through it directly. But we can reason our way back further using physics that has been checked in laboratories. The abundance of helium and lithium in the oldest stars tells us about conditions at 3 minutes. The behavior of particles at collider energies tells us about conditions at fractions of a second. Step by step, the reconstruction holds together, and it keeps holding as you go back, until you reach a time of about 10 to the minus 43 seconds. That is the Planck time. 5.39 times 10 to the minus 44 seconds, to be more precise about a quantity that resists precision of any useful kind. To give you some sense of it, the ratio between 1 Planck time and 1 second is roughly the same as the ratio between 1 second and about 10 million years, which is a duration vastly longer than the current age of the universe. It is the shortest interval that has any operational meaning in physics, because to measure a shorter one, you would need a probe so energetic that it would collapse into a black hole and hide the thing you were trying to measure. Before that moment, our physics does not give a rough answer or an uncertain answer. It gives no answer. The temperature and density climb to the point where quantum effects and gravitational effects are equally important, which is exactly the regime we have spent this whole evening establishing that we cannot describe. So when someone asks what happened before the Big Bang or what caused it, the honest response at present is not "we do not know yet." It is more awkward than that. The question may not be well formed because before requires time, and whether time existed there is precisely one of the things a quantum theory of gravity would have to tell us. Now here is what changes if we have that theory. The first instant stops being a boundary of physics and becomes a physical situation, and the candidate theories already have opinions about what it looks like, which is worth noticing. It means the question is not permanently closed, only currently unanswerable. In loop quantum cosmology, applying the discrete geometry machinery to the universe as a whole, the result that emerges repeatedly is a bounce. The same quantum geometric repulsion that stops the collapse inside a black hole stops the contraction of a universe. Run the clock backwards, and the density climbs, and then, at around the Planck density, it stops climbing. Instead of a singularity, you get a minimum, a moment of maximum compression, and on the other side, an earlier phase that was contracting. Boyevald showed this in 2001, and Ashtekar, Pavlovsky, and Singh developed it in detail in 2006. In that picture, the Big Bang is not the beginning, it is a transition, and there is a before, and the before is a universe collapsing. Other approaches say other things. Some suggest time itself rounds off smoothly, so that asking what came before is like asking what lies north of the North Pole, a grammatically fine question with no referent. Some suggest the universe tunneled into existence from a state with no classical spacetime at all. These are genuinely different answers, and they cannot all be right. But notice the shape of the change. At present we have a wall. With a theory, we would have a menu, and then, in principle, a way to choose from it. And this is the one place in the whole subject where there is a realistic prospect of evidence, which is why cosmologists care about it more than almost anyone else. The reason is that the early universe was very small and very energetic, which are exactly the conditions we cannot manufacture. It was, in effect, the only quantum gravity experiment that has ever been performed, and it left debris. If the universe underwent a period of extremely rapid expansion in its first fraction of a second, inflation, which is the leading account of why the universe looks as uniform and as flat as it does, then quantum fluctuations in the gravitational field during that period would have been stretched to enormous size and frozen in. Those frozen ripples are primordial gravitational waves. They would leave a very specific signature, a particular swirling pattern in the polarization of the cosmic microwave background, called B modes, which nothing else is known to produce in the same way. There is an even stranger thought hiding inside this, and it deserves a moment. If inflation happened, then the structures we see in the microwave sky today, the faint, hot and cold patches spread across the whole sky, the seeds from which every galaxy eventually grew, were once, before the expansion stretched them, smaller than the Planck length. Trace them backwards, and they shrink below the scale at which any physics we possess applies, which means the patterns painted across the oldest light in the universe may carry, somewhere in their statistics, a fingerprint of whatever happens at the bottom. Physicists call this the trans-Planckian problem, and it is usually discussed as a difficulty because it means the standard calculation quietly assumes that unknown physics does not spoil the answer. But it can be read the other way round. The largest structures in the observable universe grew from something that was, at one point, below the resolution limit of every theory we have. Look up at the sky, and you are looking at quantum gravity, enormously magnified, if only we knew how to read it. The energy scale involved makes this less hopeless than it sounds. Inflation, if it occurred, is thought to have happened at somewhere around 10 to the 16th giga-electron-volts, still short of the Planck energy, but only by about 3 orders of magnitude rather than 15. The early universe got closer to the wall than anything we will ever build, by a factor of 1,000,000,000. Nobody has detected them. There was a widely reported claim in 2014 that turned out to be dust in our own galaxy rather than a signal from the early universe, which was an instructive and somewhat painful episode. Experiments are continuing, from the South Pole and from balloons and eventually from space, pushing steadily down on the quantity that measures how strong the effect could be. A detection would be extraordinary, and here is why. Primordial gravitational waves would be direct evidence of the gravitational field behaving quantum mechanically. Not an inference, not an argument like Feynman's, but a measurement of a relic produced by quantum fluctuations of space-time itself. It would be, without exaggeration, the first experimental data about quantum gravity that human beings have ever obtained in 96 years of asking. It would not tell us which theory is right. It would tell us that we were asking a real question, which is more than we currently have, and it would put a number on the energy scale where the effect happened. That is the situation at the beginning of time. A wall now, a menu of answers with a theory, and one faint, real, actively pursued hope of evidence. And underneath both the black hole and the beginning, there is a third implication that is larger than either of them, because it is not about a place at all. It is about what the space between places actually is. Part 11. Space and time turn out to be made of something. The clue was there in 1972, and it took 30 years for anyone to understand what it was pointing at. Jacob Bekenstein, then a graduate student, argued that black holes must have entropy, and that the entropy is proportional to the area of the horizon. Hawking's radiation calculation 2 years later fixed the constant of proportionality exactly, and that result, which looks like a technical statement about black hole thermodynamics, is one of the most important sentences in modern physics. Here is why. Entropy is, at bottom, a count. It measures how many distinct microscopic arrangements would look identical from the outside, how much information you would need to specify which arrangement you actually have. And in every other physical system, that count scales with volume. Take a box of gas and double its volume, keeping the density the same, and you double the number of molecules and therefore double the entropy. This is so intuitive that it is hard to see it as an assumption. More room, more possible arrangements. A black hole does not obey this. Its entropy scales with the area of its boundary. Double the radius, and the area goes up by 4, not by 8. And a black hole is the most entropy you can pack into a given region. Throw more in, and the horizon simply grows. Follow that through, and you reach a conclusion that ought to be impossible. The maximum amount of information that can be contained in any region of space is set not by the volume of the region, but by the area of the surface enclosing it. Think about what that would mean for the room you are lying in. Whatever is in it, the air, the furniture, you, every atom and every field, the total number of distinct possible configurations, is bounded not by how much room there is, but by how much wall there is. The interior is somehow not carrying independent information. Everything about the inside is, in some sense we do not yet properly understand, already accounted for by the boundary. Gerard Hooft proposed this, as a general principle, in 1993, and Leonard Susskind developed it the following year. They called it the holographic principle, after the sheets of film that store a three-dimensional image in a two-dimensional pattern. And for a few years it was an interesting speculation with no concrete example. Then, in 1997, Juan Maldacena wrote down one. What Maldacena found is a precise mathematical correspondence between two theories that appear to have nothing in common. On one side, a theory of gravity, a genuine quantum theory of gravity, with strings and extra dimensions, living inside a particular kind of curved spacetime. On the other side, an ordinary quantum field theory, with no gravity at all, and one fewer dimension, living on the boundary of that space. The correspondence is not an analogy, it is a dictionary. Every question you can ask on one side has a translation into a question on the other, and the answers agree. A black hole forming and evaporating in the interior corresponds to a hot plasma thermalizing and cooling on the boundary. And the boundary theory is one whose consistency nobody doubts. It is an ordinary quantum field theory of the sort we have understood since the 1970s, and it is manifestly unitary, which is why this correspondence became the strongest argument that black hole evaporation must preserve information. Take a breath, because the implication is the largest thing in this entire subject. If a theory with gravity in a volume is exactly equivalent to a theory without gravity on the boundary, then gravity is not fundamental, and neither is the space it lives in. The interior, the dimension, the distances, the geometry, the whole apparatus of here and over there, is not a basic ingredient of that universe. It is a way of repackaging information that exists in a description with one fewer dimension and no geometry of that kind at all. Space, in that model, is emergent. It is not what reality is made of. It is what reality looks like when you organize it a certain way. And in the years since, people have worked out something of what does the organizing, and the answer is entanglement. In 2006, Shinsei Ryu and Tadashi Takayanagi found a formula connecting the two sides. The entanglement between a region of the boundary and everything else corresponds, in the interior, to the area of a particular surface. Entanglement on one side is geometry on the other. In 2010, Mark van Ramsdonk pushed the observation to its conclusion by running it backwards, and I want to walk you through what he found, because it is the most vertiginous thought in modern physics. Look at the space between your hand and whatever is beside it. Whatever that distance is, hold it in mind as a definite quantity, a fact about the world. Now, in the model, take the boundary description and start reducing the entanglement between the degrees of freedom corresponding to one region and those corresponding to the other. Not moving anything, not applying a force, simply weakening a quantum correlation. Watch what happens to the interior. The distance between the two regions grows. Reduce the entanglement further, and the distance grows further. The space between them stretches, and the connection thins, and the geometry begins to pinch. And when the entanglement goes to zero, the interior does not contain two regions that are very far apart. It contains two separate universes, with no distance between them at all, because distance is not defined between things that are not connected. Take the entanglement away, and space does not become empty. Space stops existing, which means the distance between you and the ceiling is not a primitive fact about the world. It is a statement about how thoroughly the things there are woven into each other. Proximity is a measure of correlation. The room you are lying in is not a container that happens to hold you. It is a summary of how strongly everything in it is quantum mechanically bound to everything else. Gravity is the only force that is also the room. And what we are now finding is that the room is made of something, and the something is not spatial. There is a further refinement of this that has emerged over the last decade, and it makes the picture sharper rather than vaguer. The way the interior information is stored on the boundary turns out to have the structure of a quantum error-correcting code, the same mathematical arrangement that engineers building quantum computers use to protect fragile information from being destroyed by noise. In such a code, no single piece of the storage medium holds any particular piece of the message. The information is spread redundantly across the whole system, in the correlations, rather than in any location, so that damaging any small portion loses nothing at all. And this appears to be exactly how a point deep in the interior of the space is represented on the boundary, not at a corresponding spot, but smeared across a large region, recoverable from many overlapping subsets and from no single small one. That is a remarkable thing to find at the bottom of a theory of gravity. It suggests that the reason space-time is smooth and robust, the reason geometry hangs together rather than tearing, may be that it is the output of an error-correcting process, that the room is not merely made of something, but is actively and continuously reconstructed from redundant correlations, in the way an image is reconstructed from a signal that has survived a noisy channel. The correspondence has also had a strange practical afterlife, because the dictionary translates hard problems on one side into easy problems on the other. Physicists have used a theory of quantum gravity as a calculational tool for ordinary laboratory physics, most notably to estimate the viscosity of the quark-gluon plasma produced in heavy ion collisions, where the conventional methods fail because the interactions are too strong. The prediction was close to what the experiments found. There is something quietly comic about the situation. The theory we cannot test in its own domain has been quietly earning its keep as a workhorse in nuclear physics. Now I have to be honest with you, because this is the point where popular accounts stop being careful, and I would rather not. Maldasena's correspondence is exact, calculable, and enormously well tested, and it holds in a universe that is not ours. It requires a space-time with a particular negative curvature, one that behaves as though it has a wall at infinity where the boundary theory can live. Our universe does not have that curvature. Ours appears to be very nearly flat and accelerating in its expansion, which is close to the opposite arrangement, and there is no boundary of the required kind to put the other theory on. So we have, for the first time in 96 years, a complete and consistent quantum theory of gravity. It simply describes a different universe from this one. Nobody has managed to build the corresponding statement for a universe like ours, and it is not for want of trying. Whether the lesson generalizes, whether space is emergent everywhere, or only in that special case, is genuinely open. It is entirely possible that holography is a deep truth about all of reality, and we have only found the one corner where the mathematics is tractable enough to prove it. It is also possible that it is a peculiarity of that corner. But it has already changed the field, because it converted a philosophical possibility into a demonstrated fact about at least one consistent universe. Before 1997, space might be emergent was a thing people said. After it, it was a thing people could calculate. Which brings us, finally, to the deflation. Because I have spent this part telling you what solving gravity would reveal, and I now need to tell you what it would not give you, and that turns out to matter more than any of it. Part 12. Everything it would not give us. I want to take something away from you now, because the version of this story that circulates most widely is a technology story, and it is wrong. The popular version goes roughly like this. Once we understand gravity properly, we will be able to manipulate it. Anti-gravity, warp drives, ships that fall upward, free energy pulled out of the vacuum. The theory arrives, and a century later, there are craft that do not need engines. None of that follows, and the reasons it does not follow come from the theory itself, rather than from any failure of nerve. Start with the energy. To do anything interesting with the quantum structure of space-time, you have to reach the scale at which that structure becomes apparent, and that scale is about 10 to the 19th giga-electron-volts. The most powerful machine humans have ever built, the Large Hadron Collider, operates at about 10 to the 4th. The gap is 15 orders of magnitude, a factor of 1,000 million. Let me make that concrete, because a number that size stops meaning anything when it is written down. Suppose you decide to build the machine anyway, using the accelerating technology we currently possess. You begin laying accelerator ring, you get it past the moon, and you keep going, past the sun, past the orbit of Mars, past the asteroids, past Jupiter and Saturn, past Neptune, past the point where the solar wind gives out and interstellar space begins, past the Oort cloud, past Proxima Centauri, which is the nearest other star, and you keep laying it for 10,000 years of light travel before the ring is finally long enough to accelerate a particle to the Planck energy. 10,000 light-years of accelerator. The galaxy itself is only about 100,000 light-years across. Now, that assumes present technology, and one should always be careful with such assumptions. But even the most optimistic theoretical design, a machine running at the strongest field strength the vacuum itself can tolerate before it starts breaking down into particles, still comes out at around 10 million kilometers across, which is roughly 26 times the distance from here to the moon. That is the physics-limited best case, not an engineering estimate, and nothing about it looks like something a civilization on this planet builds. This is not a funding problem. It is not a patience problem. There is no technology, proposed or speculative, that closes a gap of 15 orders of magnitude in energy. So the direct route is closed, and it is closed permanently, and any story, in which understanding quantum gravity leads to engineering quantum gravity, has to explain how a machine like that gets built. The specific fantasies fail for their own separate reasons too, and they are worth a moment because you will have encountered them. Anti-gravity, in the sense of a device that pushes rather than pulls, is not forbidden outright by general relativity, but producing it requires negative energy density in quantities and for durations that quantum field theory sharply constrains. Small amounts of negative energy do occur. The Casimir effect between two closely spaced plates is a real, measured example. But the quantum energy conditions place hard limits on how much can be assembled and how long it can persist, and every proposal for a warp drive founders on requiring quantities that exceed those limits by enormous margins. The recurring claims that anti-gravity has already been achieved and suppressed, usually attached to experiments with spinning superconductors from the early 1990s, have been the subject of careful replication attempts, including a funded effort at NASA, and no effect at the claimed magnitude has ever been found. Free energy from the vacuum fails for a reason so simple it is almost rude. The vacuum does carry energy in quantum field theory, that much is true, and the Casimir effect demonstrates it. But the vacuum is by definition the lowest energy state available. Extracting energy means falling to a lower state, and there is no lower state to fall to. The Casimir plates do real work as they come together, exactly once, and pulling them apart again costs at least as much as you gained. There is nothing there to harvest, not because we lack the technique, but because the accounting does not permit it. And here is the part that is genuinely unsettling, and it has nothing to do with technology. We now have several candidate theories: string theory, loop quantum gravity, asymptotic safety, causal sets, causal dynamical triangulations, emergent and thermodynamic approaches, in which asking for a quantum theory of gravity may be the same category error as asking for a quantum theory of temperature. Each is the work of hundreds of capable people over decades. Several are internally consistent. Several reproduce general relativity in the appropriate limit. We have no way to eliminate any of them. That is the actual state of the field, and it is why the delay matters differently than it first appears. 96 years. When I said that earlier, it sounded like a measure of difficulty, a hard problem taking a long time, the way Fermat's last theorem took 350 years. It is not that. 96 years of theoretical production, with essentially zero experimental discrimination, is a different kind of number. It does not describe how hard the physicists have found the problem. It describes how little the universe has been willing to show them. The distance side of the problem is just as bad, and it has a number attached to it that I find more sobering than the energy figure, because this one describes an experiment that has actually been performed. At the University of Washington, there is a group that has spent decades measuring gravity at the smallest separations anyone has managed. They use a torsion balance, a refinement of the apparatus Cavendish used in 1798, and their most recent result, published in March 2020, took data with the detector and the attractor separated by as little as 52 micrometers. About the thickness of a sheet of paper, Newton's inverse square law fit the data perfectly, and any new gravitational strength effect was excluded for ranges longer than 38.6 micrometers. 38 micrometers is roughly the width of a fine human hair. It is also about 10 to the 31st times larger than the Planck length. Our best direct probe of how gravity behaves at short distances stops 31 orders of magnitude short of the place where the answer lives. We are not close. We are not within sight of close. We have examined the first few steps of a staircase with 31 flights. The methodological criticism this situation has provoked deserves a fair hearing rather than a dismissal, because it comes from working physicists rather than from outside. Lee Smolin and Peter Voigt, among others, have argued that string theory in particular has absorbed an enormous share of the field's talent and funding over 40 years while producing no falsifiable prediction about our universe at any accessible energy, and that a research program in that condition has drifted away from science as ordinarily practiced. The defense is that the theory has produced verified mathematics, has generated genuine physical insight, including the correspondence we walked through in the last part, and that demanding immediate testability from a theory aimed at the Planck scale is unreasonable. Both positions have force. The honest summary is that the critique identifies a real problem and that nobody, on either side, has a good answer to it. Every previous revolution in physics was pulled forward by an anomaly, something measured that should not have been there. The ultraviolet catastrophe, the photoelectric effect, Mercury's perihelion, the null result of the Michelson-Morley experiment. In each case, nature produced a fact that did not fit, and the fact did the work of narrowing the possibilities. Quantum gravity has never had one. Not a single measurement, in 96 years, has ever disagreed with treating gravity as entirely classical. And a field with no anomalies to explain can generate possibilities indefinitely without ever converging. Which leads to a genuinely uncomfortable thought that serious people take seriously. It is entirely possible that the correct theory has already been written down, that it exists somewhere in the literature, in a paper published years ago, and that nobody can tell, because the thing that distinguishes the right theory from the wrong ones is a measurement nobody can make. There is one real hope, and it is smaller and much stranger than a collider. In 2017, two groups published independently, one led by Sugato Bose, one by Chiara Marletto and Vlatko Vedral, proposing a laboratory test that fits on a table. The logic is a piece of quantum information theory rather than a piece of gravitational physics. Two systems cannot become entangled through a mediator that is purely classical. That is a theorem, not a conjecture. So, take two very small masses, each placed in a superposition of two positions. Let the only interaction between them be gravitational. Wait. Then measure whether they have become entangled. If they have, then gravity carried entanglement, and therefore, gravity is not a classical field. That would be the first experimental evidence in the history of the subject that the gravitational field has quantum properties at all. The difficulty is severe. It requires holding objects massive enough to have a measurable gravitational effect in quantum superposition for long enough to accumulate entanglement, while shielding them from every other influence, electromagnetic, thermal, vibrational. Current estimates put the requirement somewhere around 1 million times beyond present capability, though the number keeps improving as people find better approaches. And it would not tell us which theory is right. It would tell us that the question is real. After 96 years, that would be an enormous amount. So what is left, once the technology is gone, and the collider is impossible, and the candidates cannot be separated? What actually happens when we solve it? That is the question we started with, and we are finally ready for it. Part 13. What actually happens when we solve it? Here is the answer, plainly, and then I will tell you why it is bigger than the technology story it replaces. When we solve gravity, we do not acquire a capability. We complete a description. That sounds like a deflation, and for about a minute it is. But hold it for longer than a minute, and it inverts, because of what the description is a description of. Think about what we have actually walked through tonight. 4 silences, and what arrives in each of them. At the center of a black hole, where our physics currently produces an infinity and stops, a solved theory produces a sentence. There is something there, a bounce, a core, a surface, a structure, and the word inside turns out either to refer to something or to have been the wrong word all along, and we would know which. The most extreme object in the universe stops being a hole in our knowledge and becomes a place with a physics. At the first instant, where the reconstruction of cosmic history currently stops at the Planck time, a solved theory says what happens there, whether there was a before, whether the beginning was a beginning or a transition, whether the question, what came before the Big Bang, is a real question with an answer, or a malformed question, like asking what lies north of the North Pole. And it does not merely tell us which, it tells us why. On the question of whether anything can be permanently destroyed, a solved theory settles it. Either the record survives everything, including the most complete destroyer the universe contains, or it does not, and quantum mechanics as we understand it is wrong about something fundamental. The current evidence leans one way. A theory would make it certain. And on the question of what space and time actually are, a solved theory would tell us whether the room you are lying in is a fundamental feature of reality or an emergent one, whether distance is a primitive fact or a bookkeeping device for correlation, whether the geometry you move through every day is the bottom of the stack or something assembled out of an ingredient that is not spatial at all. 4 questions that are currently not merely unanswered, but improperly posed. A completed theory converts them into ordinary questions and then answers them. That is already an enormous amount. But it is not the deepest thing, and I have been holding the deepest thing back all evening. Underneath all 4, there is a 5th question, and it is the one Einstein spent his last decade circling. He phrased it as asking whether God had any choice in the creation of the world. Strip the theology out, and it becomes this. The universe runs on about 24 numbers: the strength of gravity, the mass of the electron, the fine structure constant, 1/137, the masses of the quarks, the strength of the weak force, the cosmological constant. Every one of them is measured rather than derived. We put them in by hand because nothing in our physics explains why they take the values they do, and several of them are, as far as anyone can tell, finely balanced. Change the strength of the strong force by a small percentage, and stars do not produce carbon. Change the cosmological constant by more than a tiny amount in one direction, and the universe tears itself apart before galaxies form. Change it the other way, and it collapses. Move a handful of numbers slightly, and you get a universe in which nothing complicated ever happens. Right now, physics cannot say whether that is remarkable or not, because it cannot say whether the numbers could have been otherwise. There is no framework in which the question can even be posed. It sits in a strange limbo, discussed constantly, and belonging to no discipline. A completed quantum theory of gravity is the only thing that could make it a physics question, because a genuinely fundamental theory, one with no free parameters, no arbitrary inputs, nothing put in by hand, would either produce those numbers as consequences or it would not. And there are only 2 possible outcomes, and both of them are enormous. The first is that the numbers are forced, that the theory has exactly one consistent solution, and that solution has an electron of exactly this mass and a gravitational constant of exactly this strength, and the universe could not have been anything other than precisely what it is. In that case, there is no fine-tuning to explain, because there was never a dial that could have been set differently. And the fact that this universe produced stars and planets, and eventually something capable of lying in the dark wondering about it, that fact would not be luck. It would be a theorem. The second is that the numbers are not forced, that the theory admits an enormous number of consistent solutions, each with different constants, and we occupy one of them for no reason beyond the fact that the others do not permit anyone to occupy them. String theory currently points this way, with its estimate of something like 10 to the 500th possible vacua, a number so much larger than the count of atoms in the observable universe that the comparison is not useful. In that case, there is no deeper why. There is only a sample, and we are in it because we could not have been anywhere else. Notice that these are not two competing scientific hypotheses in the ordinary sense. They are two different answers to whether existence has a reason, and a solved theory of quantum gravity is, as far as anyone can see, the only instrument that could distinguish between them. That is what happens when we solve gravity, not a device, a verdict on whether the universe could have been otherwise. There is one more thing to say before we close, and it is a correction to a phrase that gets attached to all of this. People call the goal a theory of everything, and the phrase is badly misleading. A completed quantum theory of gravity would be a theory of the deepest layer. It would not be a theory of everything, in the sense of explaining everything, and this is not modesty. It is how physics actually works. We have had a complete theory of the electromagnetic interactions between atoms for the better part of a century. It has not made chemistry redundant. You cannot, in practice, derive the behavior of a protein from the standard model, and the reason is not insufficient computing power. It is that at each level of organization, new regularities appear that are real and lawful and not usefully expressed in the language of the level below. Temperature is real, fluid flow is real, natural selection is real. None of them are written in the fundamental equations, and all of them are true. So the completed theory would sit at the bottom, and it would leave almost everything upstairs untouched. Your morning would be identical. The tides would not change. Nothing on the surface of anyone's life would move at all. What would move is what the surface is standing on. And I would argue that is the only kind of discovery that has ever really changed how human beings understand their situation. Not the ones that gave us new powers, but the ones that told us what kind of place we are in. That the earth goes round the sun. That the species is descended and not designed. That the stars are other suns, and that most of them are unreachable. And that the light arriving tonight left before there was anyone here to receive it. Now let me close the loop we opened at the start, because the shape of this turns out to be very tidy and slightly sad, and I think rather beautiful. We have not solved gravity, because gravity is the only force that is also the room. Every other force is something that happens inside space-time, and to study something inside space-time, you can step back, set up your apparatus in the surrounding space, and look at it from outside. That is what an experiment is. That is what a measurement is. You separate yourself from the thing, and you observe it. You cannot do that with the room. There is no outside to step back into. The apparatus is made of the thing being studied. The physicist is made of it. The laboratory bench, and the light traveling from the display to the eye, and the interval between the reading and the writing down, all of it is the thing under investigation. We are trying to describe the room from inside it, with no exterior vantage point available, and there never will be one, because an exterior to space-time is not a place that exists. That is why it has taken 96 years, and why it may take a great deal longer. And it is the same reason the answer matters more than any of the things people wish it would give us. We are not trying to add a fifth force to a list of 4. We are trying to describe the medium in which every other description has ever been made. The thing that has been quietly underneath every measurement, every experiment, every thought anyone has ever had, without ever once being the object of one. So here is where we are tonight. 2 theories, both perfect, both incomplete. 4 silences where there should be sentences. A wall of energy that no civilization on this planet will ever climb. A handful of candidate answers and no way to choose between them. And a table in a laboratory somewhere with 2 very small masses on it, and a group of people trying to find out whether the space between them can carry an entanglement. That is the state of the deepest problem in physics, 96 years in. And when it is finally solved, whether that happens in 50 years, or 500, or never, what we will get is not a machine, and not a new power, and not a way to fall upward. What we will get is an answer to the question of what the room is made of, and whether it could have been made any other way. Sleep well.